Here is problem 2. Point E is at the midpoint of side CD in square ABCD, and BE meets diagonal AC at F. The area of quadrilateral AFED is 45. What is the area of ABCD? So what we know from the problem is that the area of this quadrilateral over here is 45. Other than that, point E is the midpoint of side CD. So this is our first ratio. ED is equal to EC. So how can we end up finding the area? Because we barely have any information here. Well, let's first try two things. We're going to find equivalent relationships. In other words, we're going to write a system of equations to help us solve for the variables. And second, we are going to find similar triangles. Because we have ratios and some values, we know that we're going to be looking for similar triangles or similar shapes in general, but in this case, similar triangles, because there are only triangles here. Let's first start by setting a variable. The variable that makes the most sense here is the side length, right? Because in order to find the area of a square, the only thing we need to know is its side length. So let's call it side length A. So this is A. And here we have A over 2, A over 2. After that, we need to identify similar triangles. As you can tell from our previous videos, all the pairs of similar triangles, the smaller one was inside of the larger one, like this. But in this case, it is different. If we look closely, we will see that triangle EFC and triangle AFB are similar as well. We know this because they have the same angle here, and because AB and CD are parallel, and we have the alternate interior angle theorem. It means that these two angles are the same and these two angles are the same. So they are indeed, in fact, similar triangles because they all have the same angles. So what we know is that triangles ABF and triangle CEF are similar. But now they are similar, but what is the ratio of their similarity? Well, that is very evident from our side lengths here. EC and AB are corresponding, and EC is 1/2 of AB. So the scale factor from ABF to EFC must be times 1/2. If this is 1/2, then it means that all of their corresponding features are times 1/2 as well. For example, if we were to draw the heights of each of these triangles and connect them right here, this is 90 degrees and this is 90 degrees. We can call this height x, and we can call this height 2x. But this is adding another variable, which will make it much harder. What we can do is try to represent this in terms of A, using the variable that we already have. We could call this 2/3 A, and we can call this 1/3 A. At this point, it should be pretty easy for us to find the equivalent relationship. Because we know the heights and the bases of each of these triangles, we can obviously piece them together to find the area of some portion of this square. So we know we can represent the area of the square as A squared, but we could also represent its area by doing 2 times 45 plus this triangle's area, which is 1/3 times A over 2 times 1/2. And now if we simplify, A squared is equal to 90 plus 2A over 3. A squared is equal to 2 times 45 plus A squared over 12. And that is equal to 90 plus A squared over 6. And that means 5/6 A squared is equal to 90. If we multiply 6 over 5 on both sides, we get 108. So the final answer of this problem is 108. And how surprising is that? In the beginning, we basically had no information from the problem. But from these two keys, finding equivalent relationships and finding the similar triangles and the scale, we were able to solve for the variable. So this is the final answer of the second problem.